Hello, ladies and gentlemen. Today we are going to learn about the right hand rule. In order to do the right hand rule, please locate your right hand. We'll be using this hand throughout the entire video. Let's get started. So the right hand rule first comes from this equation: F, force, is equal to Q, charge, times V, velocity, times B, the magnetic field. So what that means for us is if you have a charge Q that is moving V through a magnetic field, B is going to experience a force. Okay. Now the units for force, newtons as always. Unit for charge, capital C for coulombs. Units for velocity, meters per second. And units for the magnetic field is capital T for Teslas. All right. Now, how does this apply to our right hand? This is what I want you to do. I want you to hold your palm away from you and bring your ring finger and your pinky finger down. Okay, so your three fingers should be up. Okay, so we need to memorize which variable goes with which finger. In our equation, F is the first variable, and if we look at our fingers like this, our thumb is our first variable. F, force. Q times V is a moving charge. Okay, a moving charge we designate by our pointer finger, right? So the way I like to look at it is if you have a moving charge, you can use your pointer finger to imitate that. Bzoo, 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 right? Our pointer finger. And last but not least is our middle finger. Our middle finger is used for the magnetic field, right? Our middle finger is used for the magnetic field. And so we get F, Q, and B. All right. Now, with these three fingers, I want you to now turn your hand so that your palm is facing you. Once your palm is facing you, you are going to put your middle finger down so that your middle finger is pointing at your face. This is the proper hand position for you to use your right hand rule. And this hand position comes from this idea here. All right, so the way we properly do the equation is everything is being multiplied at right angles. Because at right angles, the moving charge through a magnetic field, if it's at a right angle, will experience the biggest force. Okay, so we are using right angles. And so between my thumb and my pointer finger is a right angle. Between my pointer finger and middle finger is a right angle. It's kind of hard to see, but between my thumb and this area here, that's also a right angle, right? So right angles everywhere. All right. B fields. We've drawn magnetic fields between two magnets before, right? It can go left to right, up and down. But sometimes we have problems where the magnetic field is either coming towards you or it's going away from you, right? And that's because magnetic fields are 3D. If the magnetic field is going away from you or into the piece of paper that you're looking at, we represent that with X's. The way I will saw it, and this is how I like to memorize it, is imagine that there's a fly and the fly goes right, and it hits your screen or it hits your piece of paper or it hits your desk. The fly's gonna die, unfortunately. And like in the cartoons, the fly will have X's over his eyes. All right. Now let's compare that to when the fly is coming towards you. Right? If the fly is coming towards you, it's alive and it has its little bug eyes. It's staring right at your face. So O's. O's for towards you, X from away from you. All right, or into the page and out of the page, respectively. Let's get some practice. All right, so get your right hand ready. Remember, thumb is force, pointer finger is direction of charge, and middle finger is the field. So I see here we have a moving charge and it's moving to the right. The field, middle finger, is going into my screen, and my thumb will now represent the force. So the force that this moving charge will feel as it's moving through this field is directed upwards. Okay, let's try that one more time. We have a charge. It's moving to the right. The field is into the screen. Yeah, and so the force it'll feel is directed upwards with your thumb. Okay, did you get it right? Good. Now, here's a very important concept. When we have a free moving charge like this, and let's say it's an infinitely big field, as soon as the charge enters the magnetic field, it's going to experience a force going upwards, right? And so the velocity is to the right, but the force is upwards. So what's going to happen to the charge? The charge is going to accelerate while moving to the right. So it's going to accelerate upwards while moving to the right. So it's going to curve like this. Now, once it curves, the force is going to follow the same pattern. And what happens is that the charge will be constantly pushed towards the middle, resulting in a circular motion. And if you remember anything from AP Physics 1, you remember that circular motion, it means that we have to use a centripetal force equation. Check out this next diagram. So we have a charge moving through a field to the right, and at that very moment, the force is directed inwards. Okay? And so because it's directed inwards, it moves to the right and it accelerates upwards. So at this point, the charge has a tangential velocity in blue, okay, going up and to the right, and the force is directed still towards the middle. So it's going to be pushed towards the middle, but it still has a velocity going in its initial direction. So at this point, the charge is moving straight up, but the force is pulling it towards the middle. Okay, and so this is going to repeat endlessly, and it's going to circle around and around and around. Cool. All right. So with that, we can come up with this equation. The centripetal force equation, which is the net force of all the forces acting along that axis, is the mass times the velocity squared divided by the radius. Okay, and the only force acting on the charge at this time is the magnetic force, so QVB. Okay, so you said it all equal to each other, and then you have the centripetal force for a charge moving in a circle within a magnetic field. Copy this one down. Good. Now let's do a couple more examples. We have a charge, point your finger, and it's moving upwards. It's moving upwards, and it has a field coming like towards my face. So my middle finger, right, field is coming towards my face. So my thumb is going to be pointing to the right. Now what that means is this charge is going to be pushed to the right. Try it out. Let's try another one. Whoa, whoa! Here we have a negative charge. So up until now, we had positive charges, but now we have negative charges. So all you have to do for this one, you're going to still use the same exact rule, except this time, watch what happens. So we have a charge, and it's moving to the right. We have a field that is going towards the screen. And so if it were a positive charge, it would feel a force going up. But because it's a negative charge, it'll feel the reverse. And so the force will actually be pointed down. Wow. How about this one? So we have a charge and it's moving upwards. The field is pointing towards you. And if this were a positive charge, it would feel a force to the right. But it doesn't because it's a negative charge, so it feels a force to the left. Wow. Amazing. Okay, well what about this one, you say? So here we have the north end of a magnet, and we have an electrical charge, positive, and it's moving upwards. The field is going to the right. And so the force it would feel will be into the screen, X. Okay? All right, let's try this one. We have a field that is moving up. The field, middle finger, is pointing to the left. And so the force, your thumb, is right at your face. So the force is directed out of the screen or towards you. And we represented that with the O's. Okay, still with me? Great. Now what about this one? We have a charge moving to the left, but wait a minute, our field is, that hurts my hand so much. The field is moving to the right. Wait a minute, didn't I say that all of our fingers have to be at right angles? Yes, I did. So because it breaks that one rule, there is no force acting on this charge. Everything must be perpendicular to each other. Okay, so you might be thinking to yourself, Mr. Lee, all of this is great. Okay, so we have a field, and the field exerts a force, and the charge moves a distance. Wait a minute, that kind of sounds like work is force times distance? Well, yes, it does. Now, is there any work done by the magnetic field? And the answer is no. There is no work done by the magnetic field because, according to the work equation, the axis of the force and the axis of the distance or the displacement have to be lined up. But what we just saw is that they're not lined up. Okay, if the force is going upwards, but it's moving to the left, this is the y-axis, and this is the x-axis. So they're not in the same axis. If they're not in the same axis, they can't be doing work. All right, let's try this one. So sometimes you'll see a wire that carries a current. Okay, now carrying a current is just like a charge that is moving, because that's what a current is. We use our right hand. The current is moving to the right. The field, middle finger, is going into the screen, and therefore F, your thumb, is going upwards. So if we have a wire with a current through a magnetic field, the wire will feel a push upwards, and it'll actually move the wire. It's a cool experiment. And for this, we use the equation F is equal to I, the current, times L, the length of the wire, times B. And B is, of course, the magnetic field. Okay, copy that equation down. Next up, we have the right-hand rule with a wire, aka this is a shape that you're going to make. You're going to hold a cup. You're holding a cup. Okay? So if a wire is carrying a current, you can determine the magnetic field by using your right hand. So your thumb is in the direction of the current, and you're going to wrap your fingers around the wire. And that's a 3D representation of the magnetic field circulating around the wire. Okay, now it's not circulating, it's there, but it's in a circular fashion. Okay, so take a look at the illustrations below. It does a great job of showing you how the magnetic field emanates away from the wire. Okay, and of course, closer to the wire, we have the stronger the magnetic field. The further away from the wire, the weaker the magnetic field. Right? Okay. In a lot of drawings, you'll see that the magnetic field is drawn as 3 separate disks or one disk, but in actuality, there's like an infinite amount of disks. So imagine the fields are on top of each other. So it doesn't really look what you see on the screen. It looks more like this. Oh, man. All right, so just disks on disks on disks on disks on disks. All right, now let's try the right-hand rule for this one. Grab a pencil, okay, or something that is long, and you are directing your thumb towards the direction of the current, and you're wrapping your fingers around this wire, okay? And so what this means is at this point, right above the wire, the field is directing away from my face or into the screen, X, right? But on this side of the wire, on the far side of the wire, my fingers are pointing downwards. So the magnetic field at that point is downwards, right? I wrap my fingers around. So underneath the wire, my fingers are pointing towards me. So the magnetic field at that point is away from the screen, O, okay? And on the other side, the magnetic field is pointing upwards, right? So it's a rotating magnetic field. It's all around, circular. Great. And so if we were to take a look at this aerially, right? So if you're looking down the wire like this, what you're going to see is that, you know, if this were a compass, the compasses all line up in a circular fashion, okay? Because the compasses line themselves up to the magnetic field. All right. Next up, we have hoops. Okay. So for hoops, what I like to do is I like to choose one location, and at that location, I do the right-hand rule for a wire, because a hoop is just a wire that is in a circular fashion. So on the right-hand side, my thumb is pointing up. Okay, to the right of the hoop, my fingers are going into the screen. But if I were to scoop my fingers around, my fingers are pointing towards me in the middle of the hoop. Okay, and so what that gives us is in the middle of the hoop or the ring, we have a magnetic field coming towards you. But outside of the ring, we have a magnetic field going into the screen, like this, and it's all around. It's really cool. And that's for counterclockwise current. For a clockwise current, you do the same thing, but it's in reverse. Okay, so choose one location. I'm going to choose the right-hand side. The current is moving down. Inside of the ring, the field is going into the screen, but I wrap my fingers around towards the outside of the ring, and it's coming towards me. Oh, great. All right, so let's go over a couple of battery rules. The convention says positive electric flows from positive to negative, and this is what we use in physics, but if you were to take some other kinds of electrical courses, you might learn the reverse. But for all of our problems, we're going to say the current goes from positive to negative. Okay, keep that in mind as we venture into the next set of rules. So the magnetic coils, you'll see this a lot. When you have a ring and you coil some wire around and around and around a ring. So basically what you're doing is you're doing circular rings or circular coils, circles on circles on circles on circles. You are making a stronger magnetic field because magnetic fields, they are vectors and they can add on top of each other, right? So the number of coils, the more coils you have, the stronger the magnetic field that is created, okay? And also if you have like a piece of metal, like an iron core in the middle of the coil, it makes the magnetic field actually a lot stronger. Okay, and it's going to look something like this, right? So let's focus down here, okay, because the current comes in this way. So I'm going to point my finger, okay, if this is that piece of wire right there, my finger is pointing to the right. I'll wrap my fingers around. And so my fingers are pointing up into the coils. Right? And that's why you see this magnetic field shooting through the coils, because the same effect goes for this point, and at this point, and at this point, and this point. Okay, they're all adding on top of each other. Right? And so we have this beautiful circular, almost like a figure 8 pattern. Okay. All right, almost finished. A couple of things to keep in mind. We did this lab in class where we created a magnet using nails, and we coiled the wire around it, the side that's attached to the positive end actually turns into the North Pole, and the side that's attached to the negative end of the battery turns into the South Pole. All right, so next time you're in class, try it. Try to see if the North Pole does in fact attract to the south side of the compass, if the South Pole of the nail actually attracts to the north side of the compass. Okay. All right, so ladies and gentlemen, that's it for the right hand rule. Rest your hand. We're going to get plenty of practice in class, but until next time, see you later.